So we're going to talk about reflection in general and then plane mirrors, which are flat mirrors. So all mirrors work off the idea of reflection. So law of reflection says that the angle of incidence is equal to the angle of reflection. Incident just means where it comes in. So it's in for incident, and then it reflects off of the surface. All angles are measured from the normal, and the normal is perpendicular to the surface. Maybe from last semester we remember the term normal, where we had to draw the normal force, where it was the line perpendicular to the surface. Same idea. So this angle and this angle, measured from the normal, will always be equal for reflection. Notice also if the object is on this side, it reflects to this side, so your image comes on the same side as the object. This is why when you look in a mirror, so just a flat mirror in your bathroom, you'll notice that your left side is on the left side of the image you see of yourself. It will always be reversed. So two types of images you can see. One is real. This is where images are formed by actual real light and you can project them on a screen. Virtual images are what you see in the mirror. So anytime you're looking in a mirror and you see yourself, that is a virtual image. So plane mirrors have flat, smooth surfaces. It's like a plane, right? Flat surface. The rays appear to come from a point behind the mirror. So the rays seem to be coming from over here. But there's no source there, right? The source is over here. So because of this, plane mirrors always produce a virtual image. So flat mirrors will always be virtual. That's why you take a flat mirror and you will see yourself. It will also be exactly the same distance. So if you are standing 1 meter from the mirror, the image of yourself in that mirror will be standing 1 meter in the mirror. And of course your left and right are interchanged. We're going to look at concave or converging mirrors. So converging just means that when light hits this mirror, it will converge together. Compared to diverging mirrors, when light hits a diverging mirror, it will bounce outward. So these are going to be for converging mirrors. So here are the fill-in-the-blank sections. If you are looking at the PDF, that way you can just literally fill in the blanks. A concave mirror is a converging mirror where the center of curvature is on the reflecting side of the mirror. So in our diagram down here, you can see that the center of curvature is on the same side as the object, so the reflective side. The other way I think of it is a concave mirror forms a cave with the reflective side. So if you put a concave mirror over your head, you would be like in a cave and you could see your reflection up in the mirror. Another example is the inside of a spoon. So the inside of a spoon, you know, is curved inward, and so that is also a concave mirror. The focal length is half the distance between the mirror and the center of curvature. So again, in our picture here, the C is our center of curvature. This is the center point. If we were to extend this circle or this mirror out into a circle, the very center of it would be C, the center of curvature. The focal point would be halfway in between. So if you know the focal point, you know the center of curvature. It's twice as far. If you know the center of curvature, you know the focal point. It's half as far. So the focal point is where all of the light rays, if they were to come in parallel to each other, they would converge at the focal point. The focal length is this distance from the mirror to the focal point. And of course the center of curvature, like we said, is the center point. A concave mirror or a converging mirror can form both real and virtual images. It depends on where the object is located. So the object is what is the thing in real life that we are making a reflection or an image of. So let's go ahead and start doing some ray diagrams. So ray diagrams are drawings that we can make to determine what the image would look like of a particular object. So here our object again is an arrow, and we're going to see if light were to hit this arrow and reflect off of this mirror, what would the image be? So in the notes it gives you the directions for how to draw a ray diagram. They are not written here, so make sure that you look at that. So light is starting on this side, and light is going to bounce off of the mirror. So this side is the real side. So if we get an image on this side, it's real. Over here is virtual. If we need to go over here, we will see a virtual image. So this would be what we would see inside the mirror. So we're going to start with our steps. So we're going to start with step 1, where step 1 says to draw an incident ray parallel to the primary axis. Yeah, so this is our primary axis. So top of the object, parallel to the primary axis. And the reflection is through the focal point, like so. Step 2 says to draw an incident ray that passes through the center of curvature. Well, center of curvature is not marked here, but we know where it is. The center of curvature is twice the distance of the focal point. So what we can do is measure our distance, which happens to be 2 centimeters, and we can stretch it out to another 2 centimeters out. So we'll mark that as our center of curvature. Move the ruler out of the way. And now we can do our step 2. Top of the arrow through the center of curvature. And you'll notice we have a spot here where the lines cross. This is where our image is going to be located. Wherever the reflections cross is where the image is going to be. So this is a real image because the light is hitting the surface and bouncing off. So this side is the real side. This side is the virtual side. And it makes sense because when you look into a mirror, you're looking into the virtual space. So this is real. To draw our image, we're going to draw it from the principal axis to the point of crossing. And I'll go ahead and make this a different color so we can see it a little bit better. There we go. So our image is real. It's also pointing downward, which means it's inverted. And all real images are always going to be inverted. If it's real, it's inverted. And the last thing is it's slightly smaller than our original object, so it's going to be reduced. So all images have a 3-step in order to describe them. So real, inverted, and reduced. Our next one says to draw a ray diagram for a concave mirror where the object is located in front of the focal point. So here's our focal point. Here's our object in front of it. So step 1, just like the first time, top of the arrow, parallel to the primary axis, and it reflects through the focal point. Step 2 deals with that center of curvature. So we need to mark that first. So 2 centimeters, which means we're going to go 2 centimeters this way again. There we go. And move our ruler out of the way. So step 2 is top of the arrow through the center of curvature. Now you should notice that these lines are not going to cross, which means we are not going to get a real image. So we're going to have to extend into the virtual space. That's where step 3 comes in. Step 3 says a virtual dotted lines are for reflected rays only. So whenever we go into virtual space, the only lines that we're going to extend are the reflections. So in step 1, we reflected through the focal point. So we can use a dotted line and extend the reflection, like so. For a center of curvature, the reflection is straight back through the center. So we're going to just extend this line. Notice we have a crossing up here. So our image, we're going to draw from the primary axis up to the point of crossing. Change that color again. There we go. And so this image is virtual. We see it inside the mirror. It is upright, which means it's pointing up. And since it's larger, we're going to call it magnified. So virtual, upright, and magnified. Example of something like this in real life would be like those bathroom mirrors, you know, the magnifying mirrors, where when you're really close to it, it makes your eyes look really big to put on makeup, or you make your eyes look really big to do eyebrows or whatever. Also for shaving mirrors, if you're shaving your face, then you need to be able to see yourself really clearly. Then you need to see a magnified image. So you would use a concave mirror in order to look at yourself in a shaving mirror as well. So some other uses of concave mirrors. One is the inside of a flashlight. So the inside of a flashlight is always very, very reflective, so that all the light that is sent out from the light bulbs that are in the center bounce off and bounce off, creating even more illumination. Another example would be a satellite dish. Notice I made sure to use DirecTV, you know, relating back to our equation. And what happens here is all of the light rays come into the dish parallel from the satellite, and they all reflect in a direction that sends it to this signal spot. And so the receiver that's right here is actually located at the focal point of this dish, so that it can receive every bit of signal from the satellite. Of course, satellite's in space. Satellite dish, satellite. And then that signal is then interpreted by the receiver, which then gives you your television. We're going to talk about convex or diverging mirrors. So a convex mirror is also called a diverging mirror because all the light rays that come in as parallel lines are going to bend outward away from the surface. They will not converge, they diverge. So here is the fill-in-the-blank section off of that PDF if you printed it off for convex mirrors. So the first thing is a convex mirror is a diverging mirror, which means that the center of curvature is on the side opposite the reflecting side. So here is the real space. So here's our object, and light is coming in from this direction. And notice that our focal point and our center of curvature are on the other side. They're quote-unquote inside the mirror. Our center of curvature is always twice the distance as our focal point, or you can also say that the focal point is half the distance of the center of curvature. The center of curvature is the spot where, if this were creating a full circle, the center of curvature would be the center of the circle. Rays leaving a convex mirror always diverge. For this reason, convex mirrors will always produce a virtual image, so always virtual, that is upright, which means it points up, and reduced. All of your images for a convex or diverging mirror will always be these three. Always virtual, always upright, and always reduced. It doesn't matter where this object is. Your image will always be over here, will always be pointing up, and will always be smaller. Some uses for this are rear view mirrors. So, you know, like the side view mirror that you've got that says objects in mirror closer than they appear. The reason why is because the smaller the image is, the further away it looks. So since it's a reduced image, then it appears to be further away. Another use is for security mirrors in stores, or even the ones around really sharp turns on the road, because by using a diverging mirror, you're creating a larger field of view. So you can see more of what's going on while you're trying to walk around a store or while you're trying to make that turn to make sure that, if you have one of the driveways that's there, you don't pull out in front of a car. So let's do a ray diagram for one of these. So now I have in my mirror and I have my ruler. So we need the ruler to figure out where that center of curvature is. The steps for drawing a ray diagram are on the PDF, so I'll just read them really quickly and then I'll show you how to do it. So step 1 says to draw an incident ray parallel to the primary axis that is reflected through the focal point. So we're going to draw a ray from the top of the object, which is our arrow there, parallel to the primary axis, which is this horizontal line. The reflection is through the focal point. Well, reflections go out. So what I'm going to do is kind of skip to step 3 in a way. I'm going to do our virtual line first. Virtual is on this side. Let's go ahead and mark that. So this is our virtual space, and this is our real space. This is real because all of the light will stay on this side of the mirror. It hits and bounces off. This is where real light is. This is virtual because no real light goes through a mirror. So our reflection is going to go outward also through the focal point. So I'm going to go ahead and do my dotted virtual line so that I can then extend it like so as a reflection. Step 2 says to draw an incident ray that passes through the center of curvature. This is where our ruler comes into play. So our ruler here tells us that this this mirror is located at 1.5 centimeters. So the focal point is 1.5 centimeters from the mirror, which means we need to go another 1.5 centimeters out to the center of curvature. The center of curvature is twice the focal length, or the focal length is half to the center of curvature. Either way you look at it. So let's mark that spot. So 1.5. There we go. And we'll move our ruler out of the way. So now we have a center of curvature. So what I would do is I would actually take my ruler here and I would rotate it so that I have it lined up with the top of the arrow and my center of curvature. That way I could draw my light rays. So top of the arrow through the center of curvature. Now our real space ends at the surface. So at this point, I need to go dotted. Anytime you go into the mirror, you have to use a dotted line. All right, so let's move the ruler out of the way now. And so now you can see that we have a spot right here where we have conversion. So our light rays converge right here in the virtual space. Otherwise, this line goes off in this direction. Our reflection from the center of curvature goes right back out along that line. So our image here is going to be virtual. So let's draw in our image. You're going to draw from the primary axis up to the point where it crosses. I'm going to change the color so that you can see this a little bit better. If I can. Alright, I might need to make it bigger. There we go. So make it red. There we go. And then I'll shrink it back down. There we go. Much better. So you can see here's our image. It is definitely virtual because it's inside the mirror. We will see this image just like a security mirror. It is pointing up. So it is upright. And it's much smaller than our original. So it is definitely going to be reduced. So all of them will be virtual, upright, and reduced.